Swayam Prabha. Digital India. Educated India.
Welcome back, students. Today we are going to start a new chapter. It's basically stress-strain relationship. So far, we are discuss the stresses and its analysis, strain and its analysis, and also the stress equilibrium equation. So let us start with the relationship between these two. I think you have studied it before. You have studied it before in your previous classes or even in also higher secondary. The basic thing you know that strain is proportional to stress. This you used to know. Now this is called Hooke's law in one dimension. So if you apply the stress and it's continuously increasing, then strain, remember that this is what I'm saying is the normal strain. Okay. So the normal strain also increases with the normal stress. So this is the normal stress. Okay. So this you already know. Now what we are going to do today, we want to generalize it for 3D. And then we will see how to bring it back into 2D. So 1D we already know. So let me start with a graph for you. Oh, this is different color. Now, this is strain and this side is stress. Or this can be force and this can be displacement. So let's say I have a cylindrical sample and I am applying the load some F and this area is A and its length is L. So this is a cylindrical rock sample of let's say some diameter 54 mm, which is the most standard one. And it has some length L. I'll talk about that length also. And its diameter, if you see, which is used to calculate the area. So there is a particular ratio we have to follow, and I will come to that. L by D ratio. Now, once I'm applying a force F, and I'm also measuring its displacement, how it is coming down. So I'm also measuring this displacement delta M. Now this can be measured using what we call the dial gauge. It's a mechanical system. And if you want to measure directly the strain, that means delta L by L, then you will be able to, I think you know, I told you, you can paste a strain gauge here. This is a strain gauge, and these two wire will come, and you can put here a Wheatstone bridge. So this will come to a box, and this will directly give you the strain, what is measured by this strain gauge. So we can directly measure the strain, or we can measure the deformation using what we call the dial gauge. A dial gauge. Okay. Now I can plot this F with respect to delta L. Here I am calling it as a U. or I can divide sigma as F by A, and strain, if I am directly measuring from here, it is one thing, and if I am not directly measuring, then delta L by L. This is the strain. So as I am applying the load, we are increasing this load. So as the delta L will increase, so F is increasing, so sigma will increase, and so as the strain. And then according to Hooke's law, because it is 1D, it should be linear. Because this relationship is epsilon is basically 1 by E sigma. I'll tell you what is E in a minute. So this is basically that constant of that proportionality. Okay, it's called the compliance, and I'll come to that. So this will look like a straight line, at least theoretically. When you come back to the campus and we'll show you the actual experiment, you will see it is not exactly the linear. There are various reasons for that, but theoretically it will be linear. So the slope of this, the slope of this is basically we call modulus of elasticity, or E. Let me write it properly. Okay, so that is that proportionality constant 1 by E. So that's called compliance, and this is called modulus of elasticity. So this is a straight line. So you heard of a term called elasticity. Can anybody define what is elasticity means?
So the ability of a material to stretch without breaking.
Okay. Anybody else? I'll take one more. Yes, talked about the ability of material to stretch without breaking. I think I will partly accept that. Either stretch or shrink, it doesn't matter. In this case, we are trying to change the shape or making it smaller. However, the main idea is when you release the load, that stretch or whatever the shrink you have done, it should come back precisely to its original position. That's why you have used the word without breaking. It means that there is no energy has been consumed for breaking the rock or for other purpose. It's just purely elastic energy which was developed in the body, and when you release the load, that energy is also released. Okay, and as a result, it precisely goes back to its original position. So that is basically elasticity. So in this case, this is purely elastic. So I am increasing the load, and if I again decrease the load in this direction, it will precisely follow this line. Then it is a purely elastic material, or we are doing a test within the elastic range. But what happens when we reach to its maximum value? When you reach to its maximum value, then it can go in many different ways. It can go this way, it can fall this way, it can abruptly fall, or it can be straight also. So there is many different paths it can go. You can see there is an infinite way it can go after it reaches its maximum value. There is a maximum value of the stress, which we normally call yield strength. We normally call it yield strength, or sometimes This yield strength is also called UCS, uniaxial compressive strength. Uniaxial compressive strength is the maximum value which it can reach. And yield, the term yield is where it departs from elasticity. That means if I have to show you in a better way, so let me delete this part and let me redraw. Let's say this is until this much is elastic. Then what is happening is they start to change its path. Say elasticity is this direction and this depart from elasticity. So up to this is elastic and this will become the yield strength. And wherever it comes maximum and then fall, so this is the UCS, uniaxial compression. So in some material, yield strength and uniaxial compressive strength are two different points. So there is a clear demarcation that it has departed from elasticity. So this linearity is lost and then it basically falls. This range we normally call the plasticity. This is basically plastic. I will come back later about this. And from here to here, we are terming it as a elastic. So up to the yield limit is elastic, beyond yield limit is plastic. And once we go to the beyond yield limit, there is four possibilities. One is stress is continuously increasing, but not as a elastic manner, not linear manner, but with strain it increases, just like steel, it does. Hardly any rock material will show that. In a uniaxial compressive strength like this kind of test, it will not show. But metal, they show the increase in stress beyond the yield limit. It continuously increases. After a long period of time, it falls. There may be a sudden drop, that is we call brittle material, and there may be a very gradual fall. This is we call strain softening. When it goes up, we call it strain hardening. When it is falling, we call it gradual fall. It is strain softening, and this is brittle. And there is a theoretical line, which basically is straight line. That means the horizontal straight line. This is called perfectly plastic. So this is brittle, strain softening, perfectly plastic, and strain hardening. So these are the four different ways after yielding it can happen. Okay. Now we come back to the equation. So let me delete a little bit. I can. So when you test, it will happen like this. So we are still in 1D. Now I will draw this little better way so that I can put some more stuff. So now this is my sample, and I told you that L by D is a very important ratio. L by D should be 2.5 to 3, in between this L by D ratio. Okay, it should lie between 2.5 to 3. There is a reason, because there is a society called ISRM. Sorry. ISRM, International Society of Rock Mechanics. They have suggested this. Now the reason is manifold. One is the stress should be developed in this body very uniformly. So that's why we need certain length, because the way we apply the load is there is a steel platen here, there will be a steel platen here, and the sample is sit in between them. Then this has a hydraulic actuator which basically come down, and this is fixed. So as a result, first, when this is the contact place between the rock and the steel platen, and due to this corner, the stress concentration is very high in the corner. But as we come little down, the stress, normally this concentration here, it is very high concentration. Then as we come down, they are becoming more or less uniform. Here also very high stress concentration. So that's why they said we need a sufficient length with respect to diameter, so that stress basically become uniform. This is one reason. And another reason is when the failure occurs, they should occur along a shear path. So if they occur along a shear path, then this is a perfect test. So means the sample will break something like this in this fashion. And as a result, we also need that length. Then only it will be considered as a perfect test. Now, if you make too small, let's say about 1.0 or something, same ratio, then this phenomena will not happen and the sample will just crash. And in that case, we will not consider it as a test for uniaxial compressive strength measurement. And if it is too long, that means if more than 3, then what will happen is this may go buckle, okay, and it may fail somewhere around here. So that is also is not expected. Is also not expected here. So that's why they have suggested, why after a lot of testing from different countries, that this should be the ratio. Then there are also restrictions on how quickly we can give the load. That means at what rate this platen should come down. So all these things are there. When you will do this experiment in our laboratory, then all these things will be explained to you in great detail. Okay, then we measure that delta L, and we measure also the load, and from that we calculate the stresses and strain, and then we in your laboratory experiment also you will plot that graph up to the failure. So there will be sigma and there will be epsilon. So from that graph you will get the UCS, uniaxial compressive strength. You can write that UCS is uniaxial compressive strength. You will also calculate the modulus of elasticity, the slope of this line, the straight part of that line. This is called modulus of elasticity. So this is a elastic property. You can see for the same UCS, the response can be very different. Okay. So one may go this way, which is very stiff. One is very soft. Okay. That means this allow lot of displacement to occur, deformation to occur before breaks. This doesn't allow much deformation before it breaks. So this basically we call this is going towards ductility, and this is kind of a brittle material. So from the nature of the value of E, also we can find out whether it will be a ductile material or a brittle material. Ductile means strain hardening. Okay, this will go above after the yielding also. Okay, so I hope you understand this part. The testing part, when you come, you will do properly. But you remember that there is a relationship between length and the diameter. You can just not arbitrarily choose. And also, while testing, there is a certain rate we maintain, and that is very small rate. What you call the strain rate? It's a almost 10 to the power minus 5 per second. So it's a very small rate we apply because it's a static testing. So the Hooke's law told us that epsilon is 1 by E sigma, or sigma is equals to E epsilon. This is, you already know. Now, I think last class or so, I have told you when we load like this, even in one dimension, when we load, the sample also increases in. Yeah, is anybody has a question? See, when it is coming down, the diameter is also increasing. Okay, so this phenomena, see, we have not applied any load here or a stress here. Just the stress is applied from the top, and this is fixed. Even in this test, we find the diameter or the area has changed or increased. Now, this phenomena was first observed by a person called Poisson, a French scientist. He has seen that, and he has termed in his name only. It's called the Poisson effect, and we also he also given a parameter, another elastic parameter called Poisson's ratio. We normally termed as mu. Now, what is that mu? The mu is equals to, we call, minus a strain occurring in lateral direction and strain in longitudinal direction. Longitudinal means this direction and lateral means this direction. It is defined at any given stress, the lateral strain, that means the strain occurring in perpendicular to the loading, divided by in the axis of the loading. The strain is occurring in the axis of the loading. And this minus sign, you can very well understand why it has been put. See, if one is compression, another is tension. So compression, if you consider positive, this is negative. So this will be negative, this will be positive. So we have to make this parameter positive. That's why this. If you are stretching, then longitudinally it will be negative, and its diameter will shrink. So that will become positive. So again, it will be positive, negative. So we have to put that negative sign. Okay. So this is what we call the Poisson's ratio, and the effect, because of a normal load, the sample also exhibits strain in its transverse direction. That means perpendicular to this loading direction. So that effect is called the Poisson effect, and the ratio is called the Poisson's ratio. This can happen at any stress level. Okay, it can happen in any stress level, but in a global sense, we write E longitudinal by E lateral. Okay, E longitudinal means in the axial direction, whatever the modulus of elasticity divided by elasticity in the lateral direction. It also defines like this, but actual definition is this. But in a global sense, in an average sense, we put it like E longitudinal by E lateral. Okay. But you will measure it using this. Okay. So there are two elastic property I told you so far. One is E. Oh, sorry, I'm deleting it. One is this E. Another is this Poisson ratio. Yeah.
So the ratios of elasticity is there with positive sign or negative. Technically negative.
Hi. Yeah. Can you repeat it again?
So the
Okay. Let me explain. I think if I understood a little bit, you are asking why this minus sign is there.
why then there is no minus sign in the elastic ratio.
Yeah. So that this become positive because this is an elastic parameter. So it should be positive. Okay. Now here, the way I have drawn, see, E lateral will be negative. The actual value will be negative value. So it may be something like this, let me tell you. The Poisson ratio may be, what I'm writing, okay. It may be minus, let's say 10 to the power minus 4 and by 5 into 10 to the power minus 3. It may be something like this. That's why it will come positive. Because this is in compression, so positive, and this is in tension, this is minus value. But we have to make it positive. That's why that minus sign is there. Okay?
Yes.
You understand? Because this is in tension. Okay, that's why. Okay, now we go to how do we utilize it in making a generalized Hooke's law. Have you heard of generalized Hooke's law in 3D? Or just this 1D thing you know so far?
No,
Okay. So now you consider a 3D body. Okay. Let me quickly draw that 3D body, if I may. And this is X, Y, and Z. So this is sigma XX. Let's say that side also sigma XX is applied. Now, how many different ways we can have strain in X direction? How many different ways I can have epsilon XX? One, I can have sigma XX by E, right? This is one dimensional Hooke's law. Now, if I have sigma YY in this direction, will it give strain in X direction? According to Poisson, yes, it will give. So there will be minus mu sigma YY by E. Now you can understand why I put minus, because this sigma YY in both direction will try to push the sample in other direction. Okay, so that's why that minus sign is coming here. Okay, similarly, I will have minus Y sigma ZZ by E. So you see that epsilon XX can come from directly from sigma XX and due to Poisson effect from these two other direction. Okay, so this is now getting the generalized form. Similarly, you can write epsilon YY. I'm just writing epsilon YY so that you understand what it is, plus sigma yy by E minus mu sigma zz by E. Okay. So this is how the strain, normal to this plane. Okay, normal strains are written. Similarly, sigma zz you can write. Now here you can see in each direction when I am writing the same E and same mu. Okay. What I'm assuming is in all directions, this elastic property, that means the modulus of elasticity and the Poisson's ratio, these two are same in all directions. If this you are assuming, say this is an assumption, okay, this assumption will be called isotropic assumption or isotropic behavior of material. This is what you are assuming, that material is isotropic. That means the property, elastic properties are same in all directions, or for that matter any other properties are same in all directions. Then it's called, that material is called the isotropic material. If this assumption is not correct, that means in some direction properties are different than the other direction. I will come to that later, maybe next class. That is called anisotropic. Okay. Anisotropic assumption or anisotropic material. Okay. Now here we are assuming the isotrope. First with isotrope. Now this happens to normal strain and normal stress. This is the relationship. Now what happened to the shear stress and shear strain? Now shear stress is normally shear strain rather, gamma is written as tau by something called G. G is also an elastic property. This is called modulus of rigidity or shear modulus. You can simply call it shear modulus, or some books also call it modulus of rigidity. Okay. Now this G has a relationship with these two properties. G is equals to E by 2 into 1 plus mu. Now I'm not going to prove it in this class, but I will request my TAs to prove that thing in their tutorial class. This is already in the book. If you do not understand, then they will explain it to you how this relationship came. You have to use the Mohr circle of stress as well as strain to derive this. But in this class, I am not spending time on deriving this equation. Since there is a tutorial class as well as book is available, so you can see from there. Okay, but the main issue is the shear strain is also related to shear stress in the same way by modulus of rigidity, and this modulus of rigidity also has a relationship with E and mu, and it is like this. So now if we combine all together in three directions, stress and strain, I will quickly write that for you. Relationship in 3D will come like here sigma xx, sigma yy, sigma zz, then tau xy, tau y z, and tau zx. If I do write this 1 by E, this you can see the first one will be 1. Here it will come. Oh, sorry. I have done mistake. This one all will be epsilon. Sigma will go that side. This is gamma. And sigma XX will be here. And so on. This will be tau ZX. Okay. So this you can see this will be 1, then minus mu 0, 0, 0, then minus mu 1.
Sir, nothing is visible, sir.
Nothing is visible.
Actually, it got stopped at the. Yeah, now it came, sir. Actually, it was a bit late.
Oh, okay. Oh,
Just check it. You can write it also.
it is coming now.
Yes, sir. It's okay, sir. Now.
Okay.
Yes, sir.
Yeah, the network has something to do with that, I guess. This one will be 2 by 1 plus 1 by mu. I think 1 plus mu by 2. Sorry, let me delete. Basically, G is E by this. So I'm just reversing it so that you understand. This is 1 by E by 2 into mu. So this is what is happening. Okay. So this is what the generalized form of stress-strain relationship, generalized form of stress-strain relationship between strain and stress. All the 6 strain tensor is given here. Epsilon, these are all epsilon. XX, YY, ZZ, gamma XY, gamma YZ. Should I write it properly? I can write it properly though. So this will be epsilon, gamma. So this is XY, YZ, and ZX. Okay. And this is the stresses. Sigma ZZ, tau XY, tau YZ, and tau ZX. So this is the relationship between the strain and the stress in 3 dimensions. All right. Now this relationship we call, if we write in a short form, this tilde is nothing but we are mentioning that this is a tensor is written in a vector form, and this is written as C. This is a matrix. Basically, this is the matrix and sigma tilde. Now this sigma is again this in a tensor form, and this is this. The C matrix is called the compliance matrix. Compliance. COMPLIANCE, compliance matrix. Okay. So this is what is called the C. So the relationship between strain and stress in 3D is given like that. This is the complete definition for an isotropic material. Okay. Now here you can see the property of this matrix. There are lots of zeros. What it means is that we still do not know, or in isotropic material, there is no way the tau xy can change the epsilon xx. There is no relationship between tau xy and epsilon xx. And similarly, in the vice versa, there will be no relationship of sigma xx for gamma xy. So this value is 0. Okay. So this is that 0 means. You can see all the diagonal positions. They are non-zero values. Non-zero values. Okay. And the matrix is symmetric. So this is called symmetric positive definite matrix. Positive definite matrix, you can find out the definition beyond of this class to explain that. But this matrix is invertible. That is what it means. Means there can be a relationship between sigma and epsilon. I can reverse the relationship also. A positive definite matrix is invertible. We can invert it. So out of total, if I see the diagonal part, out of total 21, there are 12 places are zeros and 9 places are non-zeros. And for an isotropic case, there are only two properties we are using. One is modulus of elasticity here, and another is Poisson's ratio. Is that the same matrix for anisotropic material? Of course not. In anisotropic material, these will be all non-zeros also. So actually, this is a 6 cross 6 matrix, and all 36 positions can be different in a proper definition. But for a special case, isotropic material with two elastic parameters, modulus of elasticity and Poisson's ratio, this is a very, very special case for a generalized Hooke's law. Okay. In an anisotropic, as I'm telling you, all 36 positions can be different. Okay. Again, in some cases, matrix may be symmetric. Some cases, matrix may not be symmetric also. Okay. So just mind that this is not the end of relationship between strain and stress. There is a very complex relationship exists. Now, if we invert this matrix, I think that is given in the book. I'm not writing it here, but as I'm telling you, it is also invertible. So we can write the relationship like sigma is something like D like this. So this D matrix is nothing but C inverse, and this D matrix is called constitutive matrix. Okay, you know, every country has a constitution, right? And the rules and regulations of that country is governed by that constitution, right? Here also, from there, this word has been borrowed. The material is governed by the relationship between this stress and strain, and that relationship is constitutive matrix. So that governs the behavior of the material, how that material will behave. And when you apply a load, it deforms, it creates the strain, and that strain, in other words, create the stress, and that governing factors are this D matrix, which is called the constitutive matrix. Okay, so this totally controls the behavior, how it is going to behave. Okay, so that's a D matrix or the C matrix. we use we like to use both, but D matrix is the most we use. And again, the D matrix will have 36 components, and for isotropic, again, it will be the same type of thing. There will be only 2 parameters, but for anisotropic, all 36 can be different. Okay. So this is how we are defining the behavior of material or the relationship between stress and strain in 3 dimensions. Okay. Now let me give you a very small problem from the book, which you can solve very quickly. Let me open the book and I'm giving you. Let's say a copper cable, is hanging. A copper cable is hanging in a. I'm not sure. Do you know what is mine shaft yet? Your development of DMD has started, right?
Yes, sir.
I think they probably not. Let's say this is a mine shaft, means by which we go underground. This is like a lift, okay, or an elevator. Now let's say there is a copper cable which is hanging. Okay. Now the maximum permissible stress is 8 MPa on this copper cable with a density rho. By the way, you are able to do last days that problem I gave you. It is more or less same thing. So the density is 9,000 kg per meter cube. So you have to determine what is the maximum deformation can happen to this cable. Can anybody? It is very easy. This is a copper cable hanging. Somehow it is hanging, and the maximum permissible stress is 8 megapascal. With the density of this copper is 9,000 kg per meter cube. So can anybody tell me that what is the maximum can happen if the modulus of elasticity of copper is 100 GPa? How you are going to solve? Any idea? Anybody?
So 64 by 900 meter.
Maximum deflection. What is the maximum deflection? First of all, can you tell me what is the maximum length?
800 by 9 meter, sir.
800 by 9 meter. 800 by 9. Okay, is it 90.61? Maybe you are right. Basically, let me write it down. Maybe you are right. This is given maximum. Sigma max is given. Okay. And if you have done last time's problem, yesterday's problem, then you know this will be rho g into L, right? This is the maximum stress which will develop here from where it is hanging. And that it says maximum is this. So this is giving 8 MPa. So 8 into 10 to the power 6 Pascal, it is already given. And rho is given 9000 kg per meter cube. G you can assume 10. So L you can find out. So I think you are right, probably. Okay. This is 10 to the power 6. So we can find out the L from here. Once we know the L, then we know this max will be sigma max by E. E is given. And sigma max again I know. So this is nothing but delta L by L. Now this L also I know. So you can, if you just directly put, so this will come about 7.23 millimeter. This will be the maximum deflection of this cable. Everybody understood?
Yes, sir.
Or you understood, right?
Yes.
Okay, great. Now let me give you another problem. Well, I don't like to rush because these are very basic things you must understand. Do I have time? Okay, maybe I can just give you that. Have you seen any concrete pillar while a house is being built? You know, they make pillar and tie beams. Have you seen those? Those pillars? Have you seen how they make the house? Concrete house.
Yes, sir. Yes, sir.
They say this is a concrete pillar. Now in between they put what? Let me use some other color. In between they put steel rods, right?
Iron.
Do you know how, why they put those steel rods? If they do not put those rods, what will happen to this pillar?
That may buckle.
That may buckle. Okay, no. Okay, that may be one. Basically, it gives its inherent strength. It increases in inherent strength, mostly in tensile mode, or as we said in the buckling, also in the some form of tension only. And so it increases its flexibility. Otherwise, if you put only concrete, concrete is very much brittle and steel is basically ductile. Now this problem, what is given in the book also, I have framed. It's not exactly to analyze this, but the similar thing. So a concrete pillar, and that is basically circular in shape, not this, that is circular in shape. So about 0.5 meter diameter. Okay, I'm giving you the problem. If you have book, you can see it is 5.2, example 5.2. Now this is reinforced by these steel bars or steel rods, and the combined area of these steel rods are 5 into 10 to the power minus 3 meter square. Okay, this is of the cross-sectional area of the rods, and this is of the pillar, A of the D of the pillar. Now modulus of elasticity of steel is 200 GPa. I hope you understand GPa, gigapascal, which is 10 to the minus 9 Pascal. And of that of this concrete, the other part other than the steel, so E of C is 25 GPa. Okay. Now what has happened is a 2 MPa load is applied here. 2 MPa stress is applied from the top, and this is fixed. Okay. So A is given, the total A of the rods is given, modulus of elasticity is given of both the cases. You have to consider one-dimensional problem. So 1D you will consider, and you have to determine the load carried by the steel rods. How much load? So how much Newton of load is carried by these steel rods? You understand the problem? Or should I repeat it? So the area of the pillar is diameter of the pillar is given, which is 0.5 meter. Area of all the rods are given, 5 into 10 to the minus 3 meter square. Modulus of elasticity of the steel and concretes are given. Now the question is asked, if 2 MPa stress is applied on the top, how much Newton of load is being carried by these steel rods? Okay. Now you do it in your home because we are out of time now. I give you a hint. What you have to assume, the deformation of concrete and the deformation of the steel rods are equal. You have to start there. So delta concrete is equals to delta steel. This is the basic assumption you have to do. So deformation of concrete is equals to deformation of steel. I think you start with that and use the 1D principles, stress strain relationship and the stress area relationship, all this, so you'll be able to do it. Okay. So I will see you again next week, and in between I think you will have a tutorial, and I will give you this lecture material very soon. By weekend maybe I will upload so that you can study. Okay, thank you very much.